Hello world, this is Craig. Today we're going to actually get into the 8008 assembly language, and we're going to be doing all of the instructions today. In the next video we'll actually get the assembler and start using that, but today we're going to talk about the instructions and what the assembler is doing. First of all, let's look at a program that we're going to write that is in machine language. So what we want to do is we want to make registers B, C, and D have the values 0, 1, and 2. So it's a fairly simple thing to do. So what we're going to do is load register C with 0, 1. We're going to load register B with the contents of register C, and then we're going to load register D with the contents of register C. So now everything is going to have a 0, 1 in it. Then we're going to increment register D and decrement register B. Okay, so that's simple enough. So let's go ahead and do that. The first thing that we want to do is we want to take register C and we want to put into that a 0, 1. Okay, well we know that the load instruction that we looked at earlier is going to be a 0, 0 instruction, and that's going to be, this is the load immediate, or load with the data, the following data. And so that's going to be a 0, 0, load immediate is going to end with 1, 1, 0, and then the register number goes here. So this is register, register, register. So to load register C, we look at our list, that's a 0, 1, 0. Okay, so that gives us the value 0, 2, 6. And then the next byte that is after that has to be the data that we want to load into register C, and so that's going to be a 0, 1. So 0, 0, 1. So that's a 0, 0, 1 in hex. So it's going to see this byte and it's going to put that into register C. So now C equals 0, 0, 1. Okay, so that's the first thing that we wanted to do. Now we want to put that value into register B. So we're going to just copy it from register C into register B. We know that that's a 1, 1 instruction. And then it's destination, 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 source, source, source. So the destination is B, which is a 0, 0, 1. The source is C, which is 0, 1, 0. And so that gives us a 3, 1, 2. So now B is going to equal 0, 0, 1 also. Then we wanted to put into register D that same value. So that's going to be a 1, 1. The destination is a D, which is 0, 1, 1, and the same source, 0, 1, 0. Okay, so 3, 3, 2 octal. Now, what we want to do is we want D to equal D plus 1. We want to increment it. Well, we can look, and increment is a 0, 0, register, 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 0, 0, 0, and the register is D, so that's 0, 1, 1. So increment is going to be a 0, 3, 0. And now we want B to equal B minus 1. Okay, so a decrement is a 0, 0, register, 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 0, 0, 1. And B is 0, 0, 1. Okay, so that's going to be a 0, 1, 1 is our decrement. So after we did this, D was equal to 0, 0, 1. And now we increment D, so that's equal to 0, 0, 2. And we decrement B, so now that's equal to 0, 0, 0. So this is what we finish these little steps right here, and we're going to have what we wanted, which is 0, 1, and 2 in registers B, C, and D. So as you can see, it didn't take that long to convince ourselves, hopefully, that writing code in binary is extremely annoying, and this would not be a hobby that I would care for, and it certainly wouldn't be a profession that I would want to be doing. So we're going to make this simpler, and what we're going to do is, rather than write our code in binary, we're going to create a symbol that basically performs these functions. So if we want to take and move whatever is in register C into register B, we're going to make a symbol for that. And then we're going to refer to that symbol, and that symbol is always going to just mean a 1, 1, 0, 0, 1, 0, 1, 0, so that we don't have to do that anymore. We'll let the computer do all the grunt work of converting our easy to read symbols, mnemonics, because they're memory aids for our symbols, into the actual binary code that the microprocessor needs. So let's look at what we could do for those symbols. Well, if we're the guy that gets to create the assembler, we can make it whatever we want to be. So let's talk about the one if we want to load C with the value that's in B. Okay, well, we could have a symbol. We could use a C, an arrow, and a B. I mean, that's very straightforward what's happening. So we would just have a C and some kind of an arrow and a B. We could be very explicit. We could actually, this could be our instruction, load C with B. So our instruction could be a textual instruction, and it could actually just be spelled out with what we want to do. It's prone to errors, and it takes a lot of memory, but that could be our instruction. We could abbreviate that to load register C with register B, and that would be kind of nice because if we were then doing immediate data, we could change that to something like load register C with data and then have our data, like a 0, 1, 3. And so maybe that would be our instruction if we wanted to do that. We could have just a simple command that is all of the loads, and that would operate on some data like C, comma, B. And so this would say, we would say load. Who do we want to load? We want to load C with the information that's in B. Or we could abbreviate that down to something like load C from what's in B. Okay, these are all the options that we would have, and it really doesn't matter as long as any of these resulted in the value 1, 1, 0, 1, 0, 0, 0, 1, or 3, 2, 1 in octal. So it really doesn't matter what the symbol is as long as in the end it replaces it with that value in binary, that value in octal, so that the microprocessor knows what it is that we want it to do. And as I said, the guy that writes the assembler gets to come up with what symbols he wants to use. And at any time, if you don't like the symbols that he used, you can write your own symbols and your own assembler and pick your own symbols. Okay, so let's look at that whole process. What we're going to do is we're going to create a text file. And this text file is going to have all of our symbols that we use in any data that's required. Maybe we'll have comments in this text file, but this is going to be our source file. And so it might be a .src or a .asm if we want to call it assembly, or a .08 or .08 to represent that this is for 8008. But anyway, we're going to take that text file that is easily read, and we're going to put that into an assembly program. So we're going to take that file and put it into an assembler, which is a program that's running on another computer, or if it's a different computer, a different processor, a cross assembler. But at any rate, it's going to be another program that's going to do all the grunt work of taking our symbols and converting that into the machine language. It will output an output file, and this output file may be a hex file, or it may be an octal file, but it's going to have values in here that we can just read, and it's going to be easy for us to read this output file. It may be an object file or a binary file that we can't read, but typically, and for the assembler that we're going to be using for this, it's going to be a hex file or an octal file. That output file will then go into our EEPROM programmer. Okay, so the EEPROM programmer is going to know how to open the hex file or the octal file or the whatever object file is, and it's going to program that into our EEPROM. And when it's in our EEPROM, it's going to be in binary, because our EEPROM then gets read by our microprocessor, and the only thing the microprocessor understands is binary. So this is how it's going to go from our easily readable text file through the assembler program to an output file, and then the output file is a file that we can carry around, we can look at it, but that is going to go into our EEPROM programmer that's going to open it and program it into our EEPROM in binary, because that's the only thing the EEPROM can hold is binary. And then the 8008 is going to read that binary value as if that's its program. Okay, that's the overall process that we're going to do with our assembler. So now let's start talking about what format our text file is going to be. This has to have a very specific format because the assembler program, it's going to need to be fed this data, and it has to know how to interpret and expect that data to come in. So our text source file has to be of a very specific format or syntax so that the assembler program knows how to parse each line and how to interpret that file. Okay, so what are going to be our requirements for that file? The first requirement is we're going to have one instruction per line. And we can put whatever we want on that line. And when we get to the end of that line, that is the end of that instruction. So no multiple instructions on a line. We're going to have our code, which is going to be whatever symbol we came up with before that we're going to use. And that code may need an operand, which is the data or a register value or a number that follows that code. So for example, if this is a move immediate code, where we're going to take the immediate data and put it into a register, then the operand would be the data that goes along with that code. We're going to allow a semicolon and a comment. Okay, so when it reads this one line of code, anything that is after this semicolon, it's going to interpret as a comment, and it's going to ignore everything after that. So we can have whatever we want out here in the comments. For the 8008, Intel decided the following. All instructions are going to be 3 letters, and they're going to balance the readability with the file size. And they do that by minimize the number of operands that are used and maximizing the number of unique instructions. So for example, rather than have a increment B or increment C or increment D where we have one instruction and then for the operand we put in what register we want to work on, Intel decided to do it in a much simpler way and just have each of those be represented as a single instruction. So instead of INC B, they're just going to use INB. INCC would be INC, IND, and so forth. And if you're using delimited based storage, so it's not a fixed block of storage, you know, like a punch card would be a fixed block of storage. No matter how much information you put on that line, it still is going to take one punch card. If you just have, you know, 1 byte on that line, it's going to take a punch card. If you have 80 characters on that line, it's going to take 1 punch card. So that's not delimited based storage. So if it's a delimited based storage, in this case where the delimiter of a carriage return line feed means it's the end of that line, using the operands like this is going to take less resources. It's going to take less paper tape, it's going to take less magnetic storage, it's going to take less of everything, simply because we've shortened the number of characters it takes to represent a command. We're going to use mnemonics, and a mnemonic is just a memory aid to remember the instructions. And the assembler then is going to read these mnemonics and it's going to convert that into its machine code. So these are the mnemonics for the load instructions. Remember, Intel said they're all going to be 3 characters. So load register A with the contents of register B is going to be LAB. So load A with B. Load B with A. Load the memory with A. Load A with whatever's in the memory location. Load A immediate, and immediate is going to be the next byte in memory. Load M immediate, so load our memory location with whatever happens to be the next byte that we've put into memory. If we look at the complete collection of loads, we have all of the loads for each register from any register, and then we also have load immediate from the data byte, which is the next data in memory. So we've got a load AA, load AB, AC, load A from D, from E, from H, L, from M, and load A immediate. Same for registers B, C, D, E, H, L, and M. There's only two exceptions to this table. Everything is there except we need to remember that any load of a register into itself just turns into a no-op. So if we don't want the instructor to do anything, we just do a load AA. And if we want it to halt, we do a load MM. Another thing that we're going to allow for our code is we're going to allow a label. Our format of our label is going to be a label and then a colon. And the purpose of our label is later on in our code, we might want to refer to this line of code, and rather than have to know exactly what memory line that is, we're going to give a task to the assembler to keep track of where these labels are. And when we refer to that label, it will put in that address of that line of code. So we're going to be able to put a label in. And between our portions of our line, we're going to allow any white space to delimit these. And so we can, in these, we can use either a space or a tab to separate these four portions of our code: our label, our code, our operand, or our comment. And it's much more convenient than having to have everything at a certain space. So for example, this does not have to be in column 12, or any of the other restrictions that some of the really strict languages like Fortran put on you, that things have to be in certain columns. We can just use white space. Now back to the immediate instructions. Now the immediate instructions are someplace that we can get ourselves into trouble, because with all immediate instructions, the next byte of data has to be the expected value of data. So in memory, we've got our instruction, and the byte in memory that follows that instruction has to be our data. If the data is forgotten, the CPU will interpret the next byte as data, even if it's actually the next instruction. So for example, let's say that we have the instruction load A immediate, and we put in a 0, 2, 3. Well, when it does this in memory, we're going to have the load A immediate. Load A immediate is a 006. So in our memory, we're going to have a 006, and then our data, which is 0, 2, 3. Okay, and that's fine. This is a good instruction. But let's say our next instruction, we want to load B immediate with the value, but we forget to put our value in. So our next byte in memory is going to be a load B immediate, which is a 016, and its data byte isn't there. Its data byte is actually the next instruction. So let's say the next instruction was load C immediate, and we put in 011. So that load C immediate is going to be interpreted as that next byte, and load C immediate is a 026. So what we'll put in the load C immediate is a 026, and then that value 011. And then let's say that we do a load D immediate 001, and we happen to do that correctly. So load D immediate is a 036, 011. When the program, or when the microprocessor is going through and doing this, it's going to do the load immediate and put a 023 in in A. So A is now going to equal 023, just like we expected. The load B immediate, this is going to load the next byte into the value B. So the load B immediate instruction is going to work properly, but the problem is its data is not the data you wanted. Its data is the LCI data, which is a 016. So it's going to put into B the value, 026. This is the LBI, and this is the LCI, but it's going to interpret that as the data and put that into 026. The 011, it's going to interpret as an instruction now, and 011 happens to be a decrement. 011 is a decrement, and it's a decrement B. So this is going to be a decrement B, so now B is going to equal 025. Well, fortunately, this was a 1-byte instruction, so after this, it's back on track again. Now it's going to load D immediate with the 001, so after this, D equals 001. So this got out of this little mistake as soon as it reached a 1-byte instruction. But if this hadn't been a 1-byte instruction, this would continue to misinterpret the values in memory until it reaches a 1-byte instruction so it can even itself back out again. So you can see that the simple thing of forgetting to put in the data can really mess up your program. The assembler will help us with this. When we're hand assembling, this is a fairly easy mistake to make, but when we're using the assembler would look at this and say, hey, I have no value where I should have the data that I'm going to put into that value, into that register B. So the assembler is really going to help save mistakes like this. So that's another one of the big values of using the assembler. So let's look at our instruction, which is going to be a label, our code, and our operand. And there's 4 possibilities for this. The first possibility is that the instruction is wholly contained in a single byte. So this is something like the increment or the decrement or load A from B, the load the registers, it's wholly contained in a single byte. The next possibility is that the instruction requires an additional data byte. And so those are our immediate instructions. So our load immediates, our subtract immediates, add immediates, anything that requires an immediate data after the instruction. Okay, so that would be a 2-byte instruction. The next possibility is that the instruction requires a 14-bit address. So this would be used, for example, if we're going to jump to another instruction or we're going to jump to another part of the code. So the instruction, which would be a JMP, requires 14-bit address, which is going to be represented as 2 bytes of data. Okay, so that total instruction then requires 3 bytes, 1 for the instruction and 2 for the operand. The fourth possibility is an instruction that requires a specific number or a number within a specific range. And these are, for example, if we are sending data out to a port, or if we're reading data in from a port, or if we're doing a restart. All of those things require a certain value, and there's a limit with what that value is. So for example, if we're doing an out 013, or we're doing an in 003, or if we're doing a restart 003 or a restart 006, there's only certain values that can be put in the operand for that instruction. Okay, let's just go back and look at more instructions. We have all of our increments. So we have increment B, increment C, increment D, increment E, increment H, and increment L. But there is no increment A, and there is no increment M. We have the same for our decrements. Decrement B, C, D, E, H, L. But again, there's no decrement of the accumulator and no decrement of our memory location. We have our logicals. So on the 8008, there's only 3 logicals. We have our logical ands. And so you can imagine this as a little a, because the instruction is NDA. So you can think of this as a little a, NDA, and with B, and with C, D, E, H, L, M, and immediate data. So while there isn't an increment of the accumulator or a decrement of the accumulator, there are logicals with the accumulator. We have the logical ORs, or A, B, C, D, E, H, L, M, or OR with immediate data. And again, all of those are ORing the register or the immediate data or the memory location with register A and putting the result in register A. We have the exclusive ORs, A, B, C, D, E, H, L, M, I. Sometimes we will call register A the accumulator, and that's commonly used term for the register A. Okay, look at our additions. We can add register A with any other register, and like the other commands, it leaves the result in register A. So we can A with A, which would double it. We can A with B, with C, with D, E, H, L, M, or with immediate data. If we add more than a register can hold, there's a carry just like a normal arithmetic. If we do a normal arithmetic and we have an 11 in one column, for example, we carry that 1 over to the next column. The microprocessor does the same thing, and there's a special 1-bit latch that's set to indicate that when we did a addition, there was an extra bit that rolled out of the left-hand side, and that's called the carry bit. And it's called the carry bit for kind of obvious reasons. So this carry can be added to the next addition if you're doing a chain addition using the add with carry instructions. These instructions up here, the ADA, ADB, and so forth, these were just a straight add that register or that immediate data to register A. Add with carry adds to register A the contents of the register or the immediate data that we specify, and it adds the carry if that carry bit is set. Well, it adds the carry either way. It's just that that carry will either be a 0 or a 1. And again, it leaves the result in register A. So add with carry, these mnemonics are ACA, ACB, ACC, DE, and so forth. Okay, and we can add with carry the immediate data also. Subtraction is the same thing. We can subtract any register from register A and leave the result in register A. So subtract A from A, subtract B from A and leave the result in A, subtract C from A and the result in A, D, E, H, L, the memory register, or the immediate data. Just like the carry, or if we're doing math, we can have a borrow, we can have an underflow, which results in a borrow. We have to borrow something from the column ahead. And so if we have, for example, the value 1 in the register and we subtract 1, we get 0. If we have the 0 in the register and we subtract 1, we get the value in hex FF. And the borrow would be set, meaning that there was an underflow, and so we had to have one from the column above. So the borrow bit and the carry bit are actually the same bit. We just have to keep track. If we did an addition, it's a carry, and if we did a subtraction, it's a borrow. So there's just this one bit that is both the borrow and the carry. And we, again, just like we did in addition, we can use that borrow if we're doing chain subtraction. So subtract register R and the borrow, which is the carry bit, from register A and put the result in register A. And so these are our mnemonics. A from A, subtract C from A, subtract D from A, and so forth. If we do an addition or a subtraction, and the answer happens to leave a 0 in the register, there's another special latch that is set, and that's called the 0 latch. For many instructions, if we complete that instruction and it leaves the value 0 in register A, it will set this special latch called the 0 latch. And that just indicates that there's a 0 in register A. And while we're talking about these special latches, there's actually 2 more that we haven't talked about. So in addition to the carry, which is also the borrow, or the 0, there's another one that's called the parity. And the parity latch tells us if there are an even or an odd number of 1 bits in that byte. And so if the parity latch is set to 1, it means there's an odd number of 1s in that byte. There's also a sign bit. So if the sign flag is set, it means that the most significant bit is a 1. And we do that because when we're doing signed binary, the most significant bit tells us that that's a negative number. So the 8008 has 4 of these condition bits or flags. There's the 0, the carry, the parity, and the sign. Some instructions set all of these flags. Other instructions don't set any of the flags, and some instructions set just some of the flags. So you need to look at the instruction to see which flags it's going to set. The next set of instructions we're going to look at are the comparisons. So there's a special subtraction where the result is used to set the flags, but then the result is thrown away. So in a normal subtraction, the result is put into register A and the flags are set. But there's a special subtraction where you do the subtraction, but you don't keep the result. You just set the flags. And those are the comparison instructions. So compare register R with register A and set the flags, but don't save the result of the subtraction. And so these compares are CPA, compare A with register B, compare A with register C, compare with register D, and so forth. And you can compare again with both the memory and the immediate data. So if you get confused with the compare instruction, just remember that the compare instruction is just a subtraction, and it's subtracting register R, whatever the given register is, from register A. So if the register that you're doing the subtraction from is equal to register A, the 0 flag is going to be set. So just think of it as being a subtraction, and then you can more easily remember what the flags are going to be as a result of that comparison. Rotations. We can rotate the bits in the accumulator. So there's 4 rotations, 2 in each direction, so there's 2 ways to rotate left and 2 ways to rotate right. They all affect the carry bit. So when we do a rotate, it not only affects the accumulator, but it affects the carry bit. But it affects the carry bit in different ways. And so let's look at our rotations. We're going to have a rotation, and let's say the first rotation we're going to look at, its mnemonic is RRC. Okay, and so rotate right and into the carry, but we're going to think of this as rotate right and copy. Okay, what do we mean by that? Here's our accumulator. So we have 8 bits in our accumulator, and we're going to rotate right. So we're going to take whatever comes out of every bit is going to march one location to the right, and the bit that is on the far right, the least significant bit, is going to go up and become the most significant bit. And we're going to copy that into our carry flag. Okay, so we're going to rotate right and copy. RRC, rotate right and copy. Likewise, we can do a rotate left and copy. If we do a rotate left and copy, then this bit, every bit in here is going to move 1 to the left. The one that's on the far left is going to come up and go and move in and become the bit, the least significant bit on the right. And we're going to copy that into the carry. Okay, rotate left and copy into the carry. The other kinds of rotates are RAR. An RAR treats the carry a little bit different. It treats the carry as a part of the accumulator. So in a RAR, we have all these little bits. They're all going to march one location to the right. But the one that is the least significant bit, instead of going around into the left-hand side and become the most significant bit, it is just going to go into the carry. And so this is going to be our new least significant bit. And whatever was in the carry is going to go all the way and become the most significant bit. So in this case, we copied into the carry. In this case, we rotate through the carry. And so the way that I remember these is I call this rotate all right. Okay, so we're rotating them all right. And then likewise, there's the rotate all left, which is just going to do the opposite. It's going to take whatever's in the carry, and it's going to rotate that into the least significant bit, and then whatever's in the most significant bit is going to come out and go into the carry. Okay, so rotate all of them left. So the alls include the carry in the sequence, where the RRCs only copies that value into the carry. Either copy the least significant value into the carry, if it's a rotate right, or copy the most significant value into the carry if it's a rotate left. So whichever value is coming out of the accumulator go to the other end, that also gets copied into the carry. Where the rotate alls, just imagine them as being in a line, and whatever comes out of the right-hand side of the accumulator goes into the carry. Or if you're doing a rotate left, whatever comes out of the left-hand side of the accumulator goes into the carry, and whatever's in the carry gets loaded to the right-hand side. So those are our rotates, and that's the easy way to keep the different kinds of rotates in RRC and the RAR different. Rotate right and copy, or rotate all right. Okay, those are our rotate instructions. Now let's look at our branching instructions. So normally the program just goes sequentially through memory using the program counter to keep track of which memory address it was executing. And we can do two types of redirection from this normal linear progression. So we can do a jump. Now a jump sends the program away with the one-way ticket. So we jump somewhere else and we have no intent of ever coming back to that location in the program. So to do that, the microprocessor replaces the program counter with a complete different instruction, the instruction that we have given it, and then the program just gleefully goes off to that address. Okay, and it has no intention of returning. We can also do a call. So a call is the same, that we're going to redirect the program, but now we know that when it is through with that call, it is going to come back to our next line of code. So when we do a call, it also replaces the program counter with a new address that it's going to continue the program, but before it does that, it saves the current program counter so the program can find its way back. And so this return address is saved into an internal register that's called the stack. Okay, and so we have these stack registers, and as we said in the last video, there's 7 of these 14-bit stack registers, and that is where we will stuff the address of the next instruction before we do a call. So for example, it's like a little breadcrumb that we left behind so we can find our way back. So there's 7 registers in the stack, so we can have 7 nested calls, meaning that we can do a call, and then that call can do another call, that call can do another call. We can do that up to 7 times, but the stack is a circular buffer in the 8008. And so if we do that the 8th time, then we have destroyed our original call, and we can never get back to our original call using the normal means of getting back. So we have to make sure that we don't do more than 7 calls when we're going to do this. Okay, so how do we get back from a call? So we use special instructions to get back of the call, and they're called returns. Makes sense. Because the return does something special. The return, of course, goes back to the code that we left on the stack, and then it removes that address from the stack pointer. Otherwise, we are leaving return addresses on the stack, and eventually they're going to start overwriting some of our earlier things that we put onto the stack. So the instructions for jumps and calls and returns are simply JMP followed by our address that we want to go to, a call followed by our address that we want to go to, or when we're done with our call code, we can issue a return, which then sends us back to the instruction that was after the call. So jump and call are 3-byte instructions where we have 1 instruction and then 2 address bytes. So you can go off on your own and you can learn about big endian and little endian, but suffice to say that in the assembly source code, the addresses are in the natural order. So if we want to go to address 5, in the assembly code, that operand would simply be 000-005. But when that is put into memory, these 2 bytes will be reversed. So if we looked at this in memory, it would be 005-000. Sometimes when we are doing a branch control, we want to have conditional branching. In fact, I would say most times when we're doing branch control, we want that to be conditional. So remember, we had our flags. We have our 4 flags. We have our 0, our carry, our sign, and our parity flags. So we can use each of those flags with our jumps and our calls. So for example, these are our jumps. We can jump if we have a true 0. So this jump if the 0 flag is true. We can jump if the 0 flag is false, meaning jump false 0. We can jump if the carry flag is true, jump if we have a false carry. We can call if we have a true 0, call if we have a true sign, which means it's minus. We can call if we have a true parity, which means we have an odd number of ones. We can call if we have a false parity, which means we have an even number of ones. Okay, so we have all the combinations of the jumps and calls. Likewise, we can do conditional returns. So we can return if we have a true 0, or we can return if we have a false carry. We can return if we have a false 0, and so forth. So we have a total of 3 types: jump, call, and return. There's 8 each: true 0, false 0, true carry, false carry, true sign, false sign, true parity, false parity. So there's a total of 24 commands that are for the conditional, branching, and conditional returns. All right, I mentioned these earlier, but if we have something out in the real world and we want to set a bit out there, or we want to read something in from the real world, we have input and output instructions. And so these communicate with what we call ports. And so these ports are connected to something in the outside world, and we want to exchange data between that port, meaning between the outside world, and register A. So it's important that we only are exchanging data between register A and these outside ports. And we use the INP and the out instructions. And so these are a 1-byte machine instruction, but they're a 2-byte assembler instruction since the port number is required as the operand. So for example, we have an INP001, which would get the value on port number 1 and put the value in register A. Or we would have an out 013, which would take the value in register A and send it out to whatever is hardware port assigned 013. So the 8008 can have 8 input ports. They're numbered 000 through 007, and 24 output ports numbered 008 through 031. But when we actually want to use these input ports and output ports, each input port and output port, while we will put the number in the operand of the port, that is then converted to a single byte instruction. So for example, out 025 will get converted over to the value 163 when it's fed to as the machine instruction. Likewise, in from port 5, so in the assembly we will say in, and then the operand will be a 005. The assembler will convert that to the instruction for in port 5, which is a 113 in octal. Okay, there's a machine instruction called a halt. That's HLT is its mnemonic, and it doesn't do anything until it receives a restart, or like a power on reset. And there's an instruction that does nothing, and that is a load a register with itself, like the LAA, which will essentially be called a no-op, no operation. And so the mnemonic for that, we can put in, most assemblers, we can put in a NOP, even though that isn't an official instruction. But if it doesn't accept a NOP, then we have to put in a LAA if we want to do a no-op. Okay, finally, there's these restarts that I mentioned earlier. And a restart is nothing but a call instruction with a predetermined address. While a normal call instruction has to have the instruction and then 2 bytes of the address, a restart doesn't have to have the address. We just put in a restart 0 or restart 1 or restart whatever we want. And for those restarts, it then goes to a address that is hard-coded in the microprocessor. The restarts we have, we can do a restart 0 through restart 7, And these are the addresses that it's going to go to. It'll either go through 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0. Okay, so when we put in a restart and then in the operand we put in a 4, the assembler will convert that to its instruction, which is 0, 4, 5. When the processor gets to that line of code, it will push the program counter for the next instruction onto the stack, and then it will go to the address 040, and as soon as it gets a return, it will recover that program counter from the stack and continue the program execution at that line. So essentially a restart is a call to a predetermined address, and we have to use the return to get back from that. Okay, so that is all of the instructions, and what you might want to do is either make yourself a card like this, which is a reference card, has all of the instructions on it, or you can go to Charles's website and download a PDF of this. It's got all of the 8008 instructions on the front, and then on the back it has all of the ASCII that you can also use as a ASCII and a base conversion chart. So you can go from decimal to binary to hex, octal, and it has what ASCII character it is. But the nice thing about this card is it reminds you, you can look through here and see what the mnemonic is. For example, these are all of the moves immediates. You have all of the machine instructions and I/O, the arithmetic, the branch control, logics, and restarts are here. Some information on the flags. So these are handy little summary cards for everything you need for programming the 8008. And so I would suggest that maybe you download these cards and keep a copy of it. And I'll put the link to these cards on Charles's website down below. Okay, so that's it for the 8008 assembly mnemonics. So we have learned essentially all of the things that we can do with the 8008. And as you can see, they're very fundamental types of things that we're doing. As I kind of warned you earlier, they're just simple additions, moving things between registers, logical operations, and just very simple things like that. Okay, so what we're going to do in the next video is get online and download this assembler program. So we will download the assembler program. We'll show how to do that, and there's no installation. This just runs in a DOS window. And we will start creating our text files, and we will do some simple processes where we will get from our text file to our output file. And then later we will finish the process and get it all the way back from our EEPROM back into our 8008. But for now we're going to focus on the assembler, and then we will fill out some of the bells and whistles that the assembler program has just to make our life easier when we're writing in assembly. Okay, so we're off to a good start for a second video. The third video, we will actually start writing code using the assembler, and then things will become much less painful. Okay, well, that's it for this video. I appreciate you watching, and I hope you found it interesting. And if you have any comments, of course, leave them below. Thank you. Bye-bye.